I'm Yutong, and today I'm going to talk about thermodynamic criteria for signaling. This project starts from wait, let me. Oh, I cannot click this. Okay, this project starts from a very simple observation. So let's consider the very basic setup in quantum communication, where we have a sender and we have a receiver who want to communicate via a quantum channel in between. And then we notice that to enable the transfer of information, this channel must be signaling, which means the output state depends on the input state of this channel, so that the sender can just prepare different input states and then send them to the receiver to encode some information. So from this setup, you can see the signaling quantum channels are very fundamental to quantum communication. However, if we consider a more realistic situation, then we all know quantum devices are suffering from environmental noise. And we usually assume the environment is thermal, so the noise is just the thermal noise. And from thermodynamics, we know that once we have the thermal noise, it will drive the system towards thermal equilibrium and erase the information about the initial state. So we can consider the case when the thermalization in between is so strong, so that no matter what initial state the sender sends to the receiver only gets the thermal equilibrium state as the output, so that there is no chance for the sender to communicate with the receiver. So from these two basic examples, you can see there is a tension between signaling and thermalization. So the aim of this project is actually to answer this question: how does the thermalizing tendency of a quantum channel constrain its signaling ability, and vice versa? So we note that this is different from the previous research focus in literature, where people are interested in the thermodynamic cost of implementing a quantum channel. For example, like in this paper by Philip Fast and Renate Renner, they studied the fundamental work cost of quantum processes. So in their setup, they consider a joint thermalization process described by the Gibbs preserving operation. And then by consuming some energy stored in the battery, they can simulate a local channel E applied on system X to X prime. So this kind of work cost or energy cost is well known. However, here we are not interested in the thermodynamic cost of implementing a signaling quantum channel. Instead, we want to put signaling and thermodynamic resources on the equal footing, and we want to study the interplay between the signaling and thermodynamic properties of a given quantum channel. So in this direction, there is a very recent result in this year, shows that for specific incoherent or classical setup, in the asymptotic limit, a quantum channel can transmit n bits of classical information if and only if it can transmit n units of energy. So by showing this relation, the author can construct a clear equivalence between the transfer of information and the transfer of energy in this specific setup. So our contribution to this direction is actually to give a full quantum treatment to reveal the interrelation between the signaling and the thermodynamic capacities of a quantum channel. So here in this figure, I just give you a qualitative expression of our main results. So here we consider the athermality, which just means the deviation from the thermal equilibrium. So you can understand it as a notion for the thermodynamic resource. Then
Sorry, I
from this,
needed to ask something.
yes.
So in this setting, how are you assuming that thermal states are informationless? Right? It's kind of assumption there.
Sorry, can I repeat the last sentence? How do I?
So it seems that the thermal states are assumed to be informationless. That is what you mean, that thermalization will stop you from signaling, right?
Yes.
So why do you assume that they don't have any information? For example, temperature can encode something.
Yes, so we just consider like the like the channel between the sender and receiver, and we consider the signaling ability of this channel. So and the signaling ability of this channel it is quantified by like how much the output state of this channel depends on the initial state.
So,
So
I mean, like the
yeah, I think you
temperature
would
could be
consider.
something that you wanted to say signal, then that is not a problem, right?
Yeah, I mean, for your question that you consider that you can encode some information in the temperature.
Yes.
Yeah, but that to me that sounds like you want to parameterize this channel by some parameter because this channel could depend on the temperature, and then that's like you need to use different channels with different parameters to transfer the information encoded in the temperature. So it's different from the setup we are considering.
Right. Okay.
Yeah. So here, like these quantities are all defined for a single like general quantum channel, and I will give you the precise measure for these kind of quantities. So here is just a qualitative version for the results, and we call this like the criteria for signaling. So, like the signaling ability of a general quantum channel is upper bounded by like how much athermality this channel can preserve, and is lower bounded by how much athermality this channel can transmit. So the athermality transmission is defined as the difference between the athermality preservation and the athermality generation by this channel. So this concept will be clear later in this talk. So the key message here in this slide is just to say we managed to bound the signaling ability of this channel by its thermodynamic functionality.
Also, sorry. So,
Yeah.
so athermality must depend on a single temperature, right?
Yes.
So, what is that temperature? I mean, who decides that temperature?
So you can consider like the so basically here we don't consider the temperature, but we consider a fixed thermal state as the free state. And then as long as you are different from that thermal state, then it's you will have some thermodynamic resource or you will have some athermality. So that's
Right.
temperature crisp. Yeah.
But thermal state itself is parameterized only by temperature and the Hamiltonian.
Yes. So you can consider there is a reference temperature or the background temperature for that system.
I see.
So
And then if state thermalizes at that temperature, you say that this is informationless.
sorry, what's the question? Can you repeat?
Yeah, so you fix a temperature. I mean, temperature is fixed by the setup, and once you input any other state and it gets thermalized to that temperature, then you say that it doesn't have any information.
Yes, yes,
I see. Okay.
yes. So yeah, let me be more precise about this bound. So to do that, to give you the more like precise expression of our results, I will just follow this outline, and maybe like the definition of the asthmality will be clear when we talk about the measures for asthmality and also for signaling. And then I will also give you like the physical meaning or the thermodynamic meaning of our measures. I talk about the three thermodynamic tasks associated with a quantum channel. And then we can also provide further operational meanings of these measures by considering the so-called Gibbs preserving dilation of a quantum channel. And finally, we will consider the example of quantum switch. So this quantum switch will be a perfect paradigm where we have the signaling and asymmetry and causality concurrently come into play. And our results turns out to be able to provide a full resource analysis for this quantum switch. and this will give us an application of our results. So let's just start from the first section, how to measure the athermality and settling. So to do that, I will adopt the resource theoretic framework. So the idea of resource theories is just to consider for some specific tasks, some properties of a quantum state or quantum operation can be considered as a resource. And by identifying this kind of resource, we can just divide the set of quantum states or operations into two parts. So one is the resourceless or the free state or operations, and the other is the resourceful state or operations. So for example, like the entanglement, coherence are considered as quantum resources for different tasks. And in our setup, we will consider the athermality and settling as resources. So in this figure, we have a general setup for a resource theory. So this curly S denotes the set of quantum states, and this SF is just a subset of this S. It's the set of free states. And we assume this set of free states is convex, so that it can give us many good properties. And this is a very common case in most of resource theories. And then when we have a state inside of this free set, we call this state tau is a free state. And note here, rho is outside of this set SF, so rho is a resourceful state. So having identified rho as a resourceful state, you can also ask the following question, like how resourceful this state rho is. And then to measure the resourcefulness, we need to introduce some resource measures. So in our project, we will consider the so-called robustness measure of resources. So this kind of measure just quantifies how well a state or an operation can remain resourceful under the worst case mixing with a state or an operation. So here I just give you the definition for this robustness measure, and you may find it complicated, but don't worry. In the later, I will not refer to any details in this definition. So I provide it here to just give you the intuition like how this measure works. So let's look at the definition. So it's just a minimization problem, and more technically, it's the semi-definite programming problem, which means you can just solve it efficiently by using some numerical packages. And then in this definition, we just do the convex mixture between rho and the sigma, a general quantum state. And we require the resulting state to be free, to be inside of the free set. And then we minimize the parameter S by tuning the S, sigma, and tau. So here is a pictorial illustration. So when you have two states, rho and sigma, their convex combination will just be in the line segment between these 2 points. And we require the resulting states to be inside of the free set SF. And the distance between rho and the resulting state tau corresponds to the factor S over 1 plus S. And to see this, you can see when S goes to 0, from this definition, rho will become tau. So there is no distance between rho and tau. So from this setup, you can see by minimizing S, we actually find the closest free state, tau star, towards the state rho. And in other words, this measure actually quantifies the distance between this state rho to the whole set of the free states, the SF. So if you from a more information theoretic background, you may be familiar with relative entropies. Indeed, there is a direct relation between this robustness measure and the max relative entropy. So here you just pick a free state tau and you calculate the max relative entropy of this state rho with respect to this free state tau. And then you just minimize this relative entropy over all possible free state. So from this definition, you can also see this R rho somehow measures the distance between rho and the set as f. So that gives us the meaning of the resourcefulness of this rho. So now let's just use this robustness measure to quantify the athermality for a state. So in the thermodynamic setup, the only free state will just be the thermal state. And here we consider the case for a system with fixed Hamiltonian and at fixed temperature. The thermal state gamma is fixed, and it will be the only free state. So the gamma will just be the set as f in the previous slide. And then we can define the robustness of athermality for states with respect to this free state. So basically, in this definition, we just require the resulting states to be the thermal state. And we also assume this thermal state is full rank so that we don't have any divergence in this definition. And also, this RT rho has its own thermodynamic meaning. So when rho is incoherent, this RT rho relates to the necessary work to prepare rho from the thermal state. And someone called this as a work of formation. So it's an analogy of the entanglement of formation. So this is the measure for the athermality for quantum states. And also we can consider, yes,
Sorry, so this measure doesn't depend on the Hamiltonian, right?
yes, but here in our definition, we actually don't refer to the Hamiltonian. We just pick a full rank quantum state, and we can see that there is an underlying Hamiltonian which gives you this thermal state.
Oh, that is fine, but you say that RT relates to the necessary work. So this seems strange a little bit, right? Because your measure of resource doesn't depend or doesn't care about the Hamiltonian. So it's surprising that it is related to work.
Yeah, the necessary work, actually, when people consider this kind of work of formation, they consider you attach this system with some battery system. So the battery system is just a two-level system. And then you attach, for example, you attach so the initial state is in the thermal state, and then you attach it with a battery at the excited state. And then under some thermodynamically free operation, you just transfer this gamma to rho, and your battery system go from the excited state to the ground state. So you use the energy stored in the battery system to prepare a state rho from the thermal state. So when you talk about the battery system, then you will talk about Hamiltonian, but it's simple because it's just a two-level system. Yeah, so you don't need to consider the Hamiltonian for the system. Yeah, does this answer your question?
That's it.
Yeah, okay. Yeah, then so let's just consider the how to measure the thermodynamic resourcefulness for quantum channels. Still, we need to define the set of free operations. And in thermodynamics, we all agree that the set of free operations should be like the largest set of free operations should be the set of Gibbs preserving operations, which just adds the thermal state at the fixed point. Because otherwise, if we have a channel cannot preserve the thermal state, we can just apply this channel on the thermal state, and then we will get some non-thermal output. And from this non-thermal output, we can extract some work. So that kind of channel cannot be considered as a free object in thermodynamics. So here, notice here, when we define the Gibbs preserving operations, we have a slight generalization. So this curly O denotes all quantum operations from A to B. And then we consider the input system A and the output system B could have different thermal states. And also you have the freedom to just set gamma A equals gamma B. And with this definition of Gibbs preserving operations, you can also play the same game to define the robustness of athermality for channels. So basically, you just require the resulting channel to be a Gibbs preserving operation. And notice here we use the same symbol for the channel athermality and also for the state athermality. But the types of athermality will be clear if you look at the arguments. And the reason why we use the same symbol for the athermalities will be clear later. So now, having defined the measures for athermality, let's consider the settling resource. So still, we firstly identify the set of free operations in settling, which is the set of non-settling operations. So the non-settling operations are just defined as the trace and replace channels. So they are non-settling because if you look at the definition, no matter what inputs you get, you just ignore it and then you send a constant output forward. So by this construction, there is no chance, there is no settling from the input to the output. And then we just define the robustness of settling for channels in a similar way, and we require the resulting channel to be a non-settling operation. And this RS also has its own physical meaning. So as is shown in this paper, the logarithm of RS asymptotically converges to the channel mutual information of this channel lambda. So that justifies the role of RS to quantify the information capacity of a general quantum channel. So now we have the measures for athermality and also for settling. But
So this
because we want
mutual,
to,
sorry, this
yes,
mutual information was in between the input channel and the gift withholding channel.
what's between the input channel and
Oh,
Gibbs preserving channel?
so what between what was this mutual information? This logarithm of RS.
Sorry, I don't get the question.
No, so he's asking, you have in last
Yeah,
written, right, that the logarithm of RS asymptotically converges to channel mutual information.
yes.
Yes, so he's asking mutual information between what? So I think it is reference and output of the channel.
Yeah, so the mutual information for a quantum channel is defined like so you have the system A as the input of this channel, and also you have a reference system A prime, and then you just apply this channel on. So you have a joint state, let's say a pure state psi A prime, and then you apply this channel only on the A part, and then in the output you will get a joint state rho rho A prime B, because this channel send A to B. And then you calculate the mutual information for the output state rho AB. And then you maximize this mutual information for the output state over all possible inputs state psi A prime. And then you get
This,
the channel mutual information.
so this is like classical capacity, right?
Yes, yeah, it's kind of like so I think it's defined as the entanglement assisted like information capacity, something like that in the asymptotic limit.
Okay.
Yes. So yeah, basically it's just quantifies that how well this channel can be used in the communication. Yeah. Yeah. So now we have the measures for athermality and settling, and because we also want to compare these two kinds of resources, so we need to define a joint measure which can measure these two kinds of resources simultaneously. So how do we do that? Well, if you look at the definitions of these two free sets, GPO and NSO, you can find the only intersection between GPO and NSO is a completely thermalizing channel. So this is the capital gamma here, which is a trace and replace channel, and you always replace the input by a thermal state. So by definition, this is the only intersection. And then we can just define joint measure by consider the robustness of this channel lambda with respect to this completely thermalizing channel gamma. And still, you just require the resulting channel to be the completely thermalizing channel. And then here, you get the pictorial representation for the three measures we defined. So RS as the distance between the lambda and NSO is a measure for the settling resource. And similarly, RT measures the athermality, the thermodynamic resource of this channel lambda. And this joint measure R can measure the settling and athermality simultaneously. So from this definition, it's easy to see that R is lower bounded by RT and RS. So our result is actually to find an upper bound for this R in terms of RT and RS. So here G mean is just the minimal eigenvalue of this thermal state gamma. And AB, remember A is the input system and B is the output system of this channel lambda. So from this result, you can see these three kind of resources are mutually related and mutually bounded by each other. So if you just rearrange these terms, we will you can obtain the criteria for settling. So in the middle, we have the RS, which is the settling ability of this channel lambda, and it's upper bounded by the joint resource, and this bound is trivial by definition. And then we also have the lower bound for RS, and it's also bounded by the measures we defined before, which is R minus RT. So it's good that we find the bound from both sides for this settling. So we call this like the criteria for settling. However, so far what we get is just the mathematical inequalities, but we are doing physics. And recall that the name of this talk is thermodynamic criteria for settling. So the next question is, how do we interpret these bounds, and can we give any physical meanings for these bounds? So to do that, now let's consider the three thermodynamic tasks. So given a quantum channel, there are three tasks you can ask this channel to do in thermodynamics, which are the generation, the preservation, and the transmission of athermality. So let's consider the first one, the athermality generation. So we ask how much athermality can a channel lambda generate from the thermal state. So in this figure, I used the battery to denote the amount of athermality. And clearly, once you have the empty battery, it corresponds to a thermal state. So in this setup, we have this result. So the athermality of a quantum channel is equivalent to its athermality generating ability. So if you look at this equality, the left-hand side is just the channel athermality, and the right-hand side is the athermality of the output state when this channel is acting on the thermal state. So that means the thermodynamic resourcefulness of a quantum channel is just equal to the thermodynamic resource this channel can put into the thermal state. And this equality also gives us an equivalence between the channel athermality and the state athermality. Is why we use the same symbol for the channel athermality and also for the state athermality, because the channel athermality can always be reduced to a state athermality. So with this result, we can conclude that the task 1, the athermality generation, is quantified by RT. So now let's consider the second task, the athermality preservation. So we ask the question, how much athermality can this channel lambda preserve when it's acting on one part of this pure locally thermal state, gamma tilde. So here, one of the choices of gamma tilde is just given in this way. So someone called this as the thermal field double state. And basically, it's just like the standard purification of a thermal state. So gamma tilde is locally thermal, which means if you look at the marginals, you only get the thermal state. However, because gamma tilde is pure, so it has some global athermality. And then we apply this channel only on one part of this locally thermal state. And then we ask what's the overall athermality we get as the output. And we call this overall athermality as the output the athermality preservation. So you may wonder, why do we call this athermality preservation instead of another kind of athermality generation? Because by applying this channel lambda on this locally thermal state, maybe you could also generate some athermality from this locally locally thermal state. Well, to exclude this situation, we actually have this no-go relation. So we can show that no local channel can increase this overall athermality from this input computer. So that means the overall athermality you get as the output can only be equal or less than the athermality you put in the input. And this equality holds if lambda is unitary, and this inequality holds for all quantum channels. So with this, we can show the athermality we get at the output is really the athermality we preserve from the input. And this also justifies the choice of this gamma tilde because it gives us the best test bed to really single out the athermality preserved by this channel. So now we find that the output overall athermality we get at the output is also equal to the joint resource of this channel lambda. So with this equality, we can conclude that the athermality preservation of this channel lambda is quantified by this joint measure R. So now let's consider the final task, the athermality transmission. So instead of ask how much athermality this channel can preserve from this gamma tilde, we ask how much athermality can this channel transmit from this gamma tilde. So notice that although the overall athermality cannot be greater than the initial athermality, this channel is generally resourceful in thermodynamic sense, so that it can generate some local athermality to the system B. So to quantify the athermality transmitted, we actually need to do a bit accounting. But the accounting is still very simple, because we already have the two previous tasks. So the transmitted athermality is just given by the athermality you preserve in the output minus the athermality this channel generated locally in this system. Because when this preserved athermality minus the athermality generated, the rest of athermality can only come from the input, and this corresponds to the transmitted athermality. So with this, we can conclude that the task 3, the athermality transmission, is quantified by R minus RT. So now let's do a summary. Let's make a summary. So the first task, athermality generation, is quantified by RT, the athermality of this channel. And the athermality preservation is quantified by R, the joint resource of this channel. And finally, the athermality transmission is given by R minus RT. So now let's go back to our previous criteria for signaling, and we can give them the full thermodynamic meaning for this bound. So still in the middle, we have the signaling ability of this channel, and it's upper bounded by this R, which corresponds to the athermality preservation. And in this lower bound, in the square bracket, we have the athermality transmission, which is given by the athermality preservation minus the athermality generation. So with all of this, we can conclude that this is the thermodynamic criteria for signaling. And I also want to emphasize that this criteria is full quantum. So like everything are just defined for a general quantum channel. And you can see how the signaling ability of a quantum channel is constrained by its thermodynamic capabilities. And also here is the again the pictorial representation for our results. And now you will be familiar with these batteries, and you can see how these batteries come from these three thermodynamic tasks. So this is our main result. And also we have one remark. So if you look at this bound, and one lambda is a Gibbs preserving operation, because we know Gibbs preserving operation cannot generate any athermality. So for GPOs, athermality transmission will be equivalent to athermality preservation. Then we can just rewrite this joint resource R for GPO as this quantity PTG. So it's just redefine this R of G for GPOs. And we call this PTG as the athermality preservability for a GPO. And then you can see this bounds reduced to this one. So the settling ability of this GPO is bounded by the athermality preservability from both sides, which means once your GPO can preserve some athermality, then this GPO must be able to signal, and vice versa. So we also notice that this athermality preservability, this PT, corresponds to the previous measure defined in this paper, resource preservability. So in this framework, the author considered the general quantum resource theory. And then because we know the free operations in resource theories cannot generate any resources when applied on a free state. So the author asked, if you just apply the free operation on some resourceful state, how much resource this channel can preserve from the input resourceful state? And to quantify that, he gets the notion of the resource preservability. And here our PT defined for GPOs is just a measure for athermality preservability. But recall here, from our previous thermodynamic tasks, this R also measures the athermality preservation, but for a general quantum channel. So with this, we can conclude that our joint resource measure R is actually a generalization for this PTG for all quantum channels. And if you and by relating this R with this PTG, we can actually give a further operational meaning for this joint resource measure. And this leads to the so-called GPO dilation of a quantum channel. So we all know the unitary dilation or the system environment dilation for a quantum channel. Basically, it says that given a quantum channel, you can always consider it as you can always consider you have a system tensor product with some environmental state, and then you apply the joint unitary on both systems, and then you trace out the environment. So here we consider a similar setup, but we just replace the joint unitary by a joint GPO. And note that different from unitary dilation, here we don't require G to be unitary. We just require G to be a GPO. And this still corresponds to the previous case we mentioned, the fundamental work cost of quantum processes. So in their setup, they consider you to use the Gibbs preserving operation to simulate a channel E by using some work or energy stored in the battery. So here, we also want to simulate a general quantum channel lambda by using the GPO. But what we consume here is actually the athermality we defined, stored in this state rho at system C. And how this relates, how this setup can relate our resource measures. So let's firstly focus on this GPO in this GPO dilation. And then we can define the set of GPOs which can simulate or dilate lambda. And then we find that if you consider the minimal athermality preservability of this kind of G which can simulate lambda, then this minimal PT is bounded by is lower bounded by this R, the joint resource of this resulting channel, and it's also upper bounded by the maximum between 1 over RT of this resulting channel and R, the joint resource of this resulting channel. So this looks a bit complicated, but once you have this condition satisfied, then the upper bound just reduced to this R. Then this minimal athermality preservability in this GPO dilation is bounded by R, the joint resource of this channel lambda from both sides. So we can conclude that for a general quantum channel lambda, its joint resource just equals to the minimal asymmetric preservability you need to pay in this GPU dilation once you have this condition holds. So this gives us a clear relation between PT and R. And then this also justifies why this joint resource R can be understood as the asymmetric preservability for a general quantum channel lambda, because it usually comes from the asymmetric preservability for its parent channel G in this GPU dilation. So we know that we only have this minimal dilation condition when this condition holds. So we can also study like how universal this condition is. And to do this, we just do some numerical investigation. So we consider the random qubit channels. So we plot them in this figure when where the x-axis is just the RT, the asymmetry of a quantum channel, and the y-axis is just the signaling robustness of a quantum channel. And each random qubit channel is plotted as a dot here in this plot. So the joint resource of this channel is labeled by this color bar. So because non-signaling operations has no signaling resource, so they are all on the x-axis. And similarly, our GPOs are on the y-axis. And the intersection, the completely simulating channel, will be at the origin. So from this figure, we can also find the most resourceful channel in the signaling sense will be the unitary channels, because unitary channels are reversible. So you will not lose any information about the input state. So they have the highest signaling resource. And also in thermodynamic sense, the most resourceful channel will be the most energetic channels. Those are channels which can map the thermal state to the highest energy eigenstate, because the highest energy eigenstate corresponds to the highest energy you can get from this system. So these are the most thermodynamically resourceful channels. So in this plot, once we just check if this condition holds. So if this condition holds, then we just give a black frame color for this dot. And when this condition doesn't hold, we just use the blue color to denote this dot. And here we plot the 20,000 random qubit channels. And we find this condition is satisfied by 88.2% of these quantum channels. So that means this condition is commonly held. However, we still have some area which is the blue corner here, where this condition doesn't hold. But it doesn't mean that we don't have this minimal dilation condition for this blue corner. It's just that so far we cannot prove this. So it's still an open question for the future investigation. And then let's consider the other elements in this GPU dilation. So we have considered the channel G. Now we consider the state rho C here. So still we consider the set of rho C which can simulate or dilate lambda. And then we find that for any quantum channel lambda, the asymmetry of this channel corresponds to the minimal asymmetry you need to pay in this GPU dilation, corresponding to the minimal asymmetry in this state. So again, this relation tells us there is an equivalence between the channel asymmetry and the state asymmetry. And we always get this minimal dilation for all quantum channels without any further or extra conditions. So now let's summarize the results. So as you can see here, we consider the joint resource and the asymmetry for a quantum channel, and they can always be linked to some resource you pay you invest in this GPU dilation. However, these two are different because R and RT inherit different types of resources in this GPU dilation. R corresponding to the asymmetric preservability and RT corresponding to the asymmetry. So now let's consider let's go to the final section, which is the application of our work, and we will talk about quantum switch. So what is a quantum switch? Well, it's just a platform which can realize the superposition of causal orders of quantum channels. And the idea is very simple. So if you consider you have a system and you have a control qubit. So when the control qubit is in 0 state, you firstly apply omega 1, the first channel on your system, and then apply the second channel on your system. And when your control qubit is in 1 state, you firstly apply the second channel and then the first channel on your system. And because in quantum mechanics, we are allowed to have superpositions between 0 and 1. So when this control qubit is in the superposition between 0 and 1, then this system will undergo the so-called indefinite causal orders of the quantum channels. And to realize this, you can just consider the cross operators when you have the omega 1 and omega 2 as the input channels. So the cross operators of the quantum switch with these two inputs can be written in this way. So you have the control system, and then K1, K2 are the cross operators for the first channel and the second channel. So with these cross operators, you can see once you have some coherent states in your control, then you will have some mixture for these cross operators. Also, if you like to have a more formal understanding or formal interpretation of this quantum switch, you can just consider it as a higher order quantum map. So here you just have two channels as the input, and the output of this quantum switch will just be another quantum channel acting on system A, C to system B and C prime. So why this quantum switch is interesting? Well, because it has applications in settling and also in thermodynamics. So for the settling part, people find that by using the quantum switch, you can get some activation in settling. So that means if you consider the input channels are just the fully depolarizing channels, where you just have the trace and replace channel, and you always replace your inputs by the maximally mixed state. And clearly, if you have the definite causal order, so you just apply this channel phi sequentially, then the resulting channel will still be non-settling. So your output state will still be independent of your input. However, people found that once you have the coherent control of these causal orders, i.e. when you use the quantum switch, and then by simply superposing the causal orders of these two channels, the output on system B and C prime will depend on the initial state of this system A. So people call this the settling activation because you rarely can activate a non-settling channels to a settling channel by using this quantum switch. So that's the application of quantum switch in settling part. And also people also studied the thermodynamics of quantum switch. So they consider that with the quantum switch, and if you input two Gibbs preserving operations, so still let's consider the definite causal order. If you just apply this Gibbs preserving operation twice, then the whole thing will still be a Gibbs preserving operation. So once you have a thermal input, you will still get a thermal output. However, if you use the quantum switch and with this coherent control, people find that if you look at the system B and C prime, you will get some non-thermal output, although you only have the thermal input in the system A. So with this, you may wonder, well, does that mean that the quantum switch can violate the second law of thermodynamics? Well, the answer is clearly no. And as identified by this paper, if you have the quantum switch with two Gibbs preserving operations as inputs, then the whole thing will be a Gibbs preserving operation. And then let's look at the input system A and C. Because to use the switch, the C must be coherent. Then the coherence will be a thermodynamic resource. So it's natural to have some non-thermal input via a free operation to get some non-thermal output. So there is no violation for the second law. But from this example, it also inspires us to actually look at the resource of this quantum switch. So we want to analyze where this resource come in and where the resource come out. So to study this signaling and athermality property of this quantum switch, we consider the quantum switch as a channel simulation problem. So if you look at the quantum switch plus this control system, then what you get is just a new channel lambda s acting on system A to system B and C prime. And then we just ask how do the signaling and thermodynamic properties of the channel lambda s depend on the input resources. So the input resources will be the inputs control and the input channels. So to make the physics more clear, let's consider the specific setup. So we have this control system rho C to be in the pure state, where we use this parameter alpha to control the superposition between 0 and 1. And because we don't want to have any preference on which causal order in this quantum switch, so the thermal state of this control system will just be the identity. And then we assume gamma A and gamma B are equal. Then we consider this specific Gibbs preserving operation, which is just the convex mixture between the completely thermalizing channel and the identity channel. And S is just the thermalizing strength. So when S equals 0, we do nothing on the system. And when S equals 1, we have the full thermalization. So with this setup, here is just a list of our results, and we will go to them. We will go to them one by one. So don't worry about this kind of bounds. The take-home message here is just like if you look at the three quantities highlighted in red, these are the three resources we talked about before for the resulting channel lambda s, and they are all either bounded or analytically expressed. So with this result, we can conclude that we have the full resource accounting for this quantum switch. So now let's look at the first one. So we find that the joint resource of this channel lambda s is upper bounded by the input resources of this quantum switch. So the input resources will be the athermality of this rho C, and also because these two are GPOs, so they will have some athermality preservability. And remarkably, we find that when S goes to 0, then this G will be identity. So we have this R exactly equal to the input resources, RT rho C plus 2 PTI. So this factor 2 comes from the fact that we have two channels input into this quantum switch. And also when S equals 1, then G will be the completely thermalizing channel. So this channel has no athermality preservability. So the joint resource will just be the athermality of this rho C. And then let's consider the criteria for signaling we derived before. So if you look at the lower bound, because this joint resource is upper bounded by the input resources, so it's kind of fixed. And when this is constrained by the input resources, then this lower bound actually tells us there is a trade-off between RT and RS. Because when RT goes up, then RS will go down, and vice versa. So to see this trade-off between the athermality and signaling for this channel lambda s more clearly, let's consider this specific case. When S equals 1, so G becomes the completely thermalizing channel. Then we have this joint resource equals to the athermality of this rho C. And we call this term RT rho C minus RT lambda s the athermality waste. Because if you look at this setup, you can still consider this as a channel simulation problem where you just use this joint GPO with some state rho C to simulate this channel lambda s. And recall, previously we have this minimal dilation condition. So to simulate this channel lambda, the best or the optimal case, you just need to pay the same amount of athermality in this state, rho C, to simulate this channel. So once you pay more, you will get some athermality waste in this channel simulation. However, this bound tells you that once you have this athermality waste, then you will also have some non-zero settling in this resulting channel. In other words, we can see this settling of this resulting channel is activated by non-zero athermality waste. So with this statement, you can see there is a clear trade-off between RS and RT. And here, the final slide for this section will is just to give you the example. So we consider the qubit systems A and B with the fully degenerate Hamiltonians. So the thermal state will just be the identity. And here are how the parameters are defined, and these two are our bounds. So for this plot, the left-hand side plot, we fix S to be 1 and we vary alpha, the superposition strength. So we can see in this case R is a constant, and when we increase alpha, when we turn on the switch, then we will have some athermality waste given by R minus RT here. And once we have some athermality waste, we will have some activation in this settling. So by showing this, you can see there is a clear trade-off between RT and RS. And similarly, for this plot, we fix alpha, and then we change the thermalizing strength S. So although in this plot, both RT and RS are decreasing because the joint resource R is decreasing. However, you can still find there are some complementary behaviors between RS and RT. So still there reflects their trade-off behaviors. So now with all of this, I want to summarize this talk. So in the first place, we defined the three resources matters for a general quantum channel lambda: the settling robustness, the athermality or the thermal robustness, and the joint measure for settling and athermality. So with these three measures, and we consider the three thermodynamic tasks, we can give the thermodynamic criteria for settling. And then we consider the GPO dilation of quantum channels. By considering this kind of setup, we can we find that this joint resource R and RT of this resulting channel lambda inherits the input resources in this GPO dilation. And they are correspond to different types of resources you need to pay in this GPO dilation. And finally, with this result, we can do a full resource analysis of quantum switch and reveal there is a trade-off between the settling and athermality of this resulting channel lambdas. So for the future directions in this work, firstly, someone may argue that the Gibbs-preserving operations are not very physical. So you could consider more physical thermodynamically free operations, for example, the time covariant GPOs or thermal operations. So note that this kind of operations, they are all subsets of GPOs, and all RT is defined with respect to GPOs. So if you redefine RT with respect to the subset of GPOs, you will just get a higher RT. And with a higher RT, you will just get a further lower bound. So that means all results will still hold for this kind of free operations, although you will get a looser bound if you change the definition. And the next direction is to consider the higher order quantum maps. So we can ask the question like, what's quantum supermaps which do not increase the sum of these resources, RS plus RT, but can actually exchange them. And finally, you can also consider other resource series with intersection between their free sets. And maybe our approach can also be applied in that setup. So that's all. And thanks for your attention. And I'm welcome to any questions.
Thank you, Yutong. Any questions from the audience? Okay, I think there were questions in between, so perhaps, yeah, just like some observation when you were discussing about this intersection of GPU and replacer channels, like Gibbs preserving operations and the set of replacer channels. Recently, it has been shown this maximum entropy principle that the thermal channels, like the replacer channel, which only outputs thermal state, has the
Hmm.
maximum entropy.
Yes,
Okay,
I
like
think I have seen this kind of result. Is this your paper? Like you prove that this gamma, the big gamma
yeah.
is the is the maximal and has the maximal entropy, right?
Yeah, so does that have like, yeah, so the entropy, I mean, can, like right now you have in terms of divergence, right? So in some sense, do you see any direct connection with the entropy of the channel with the signaling? Because you can write it also as the minimum output conditional entropy of the channel's output. So that also has some role with the signaling, right? Like let's say whether from the environment and the thermodynamic capacity, like the paper that the entropy of the channel is equal to thermodynamic capacity of its complementary channel. So this is result by Philip Fest and Sumit Khatri. Like they made this observation recently.
Okay. Yeah, I'm not quite sure about their results. Like when you see the thermodynamic
Okay.
capacity of a complementary channel, I don't know that.
Okay. Yeah, because I see that your work, I mean, since you are interested in signaling and all, and then there is role of how isometric extension may behave. But what was peculiar was you were looking at the intersection of replacer channel and Gibbs preserving operation, which is thermal channel, like
Mhm.
replacer, like thermal channel, which completely replaces all input to the thermal state, and that turns
Yes.
out to be the one with maximum entropy, right? So if there is any interpretation in that sense, because you are looking at the divergence with respect to those that specific channel. So that was
Mhm. Yes. So I'm not sure that the entropy of a quantum channel also has some meaning in the signaling side.
it will have in the sense like it depends. So if you have replacer channel, then the entropy of the channel is always positive. It's not negative. Okay, and in that sense, one can say that there is no signaling from the environment to the output of the channel also, like in that sense. Or even if there is a reference system, then reference systems, it is entanglement breaking. So you can talk about PPT, like the output of the channel with reference, whether it is PPT or product. So something like, so it does have, but I was like thinking that if you take this constraint of energy constraint, like the constraint on energy, because then thermal state is the one with maximum entropy. And if it does say something, but okay, like just an open question, nothing specific.
Yeah, I see. Yeah, I will have a look about Philip
Hmm.
Fast's paper, maybe. Yeah.
So
Okay.
I had some doubts while I'm
Hmm.
following the talk. I don't feel anything related to the thermal state here. So you say that thermal state and gives preserving and so on, but I don't see. I mean, I can do all these things just by taking some fixed state as my free state, which is not thermal,
Yes.
and some operation which is having this state as fixed point. Every result will go through because you didn't consider any geometric distribution or Hamiltonian or anything. Do you think it's true?
Yes, because like I think your setup can be applied to like any Gibbs state, because what we are considering, actually you just pick one full rank state in your set,
Yes.
in your whole set of quantum states,
Yes.
and because it's full rank, so you can always take the log of it to solve out
Yeah.
to figure out a Hamiltonian, which gives you this state as a Gibbs state.
Yes. So
So
that
yeah.
connection seems like enforced connection. So it doesn't seem natural to talk about thermodynamics with fields because I can, I mean, not all full rank states can be mapped to thermal state if I fix Hamiltonian. So
Yes.
Hamiltonian I cannot have arbitrary. So I have to like have some physical meaning behind the Hamiltonian, then not every full length state can be mapped to a Gibbs state. but I can still apply this formalism. So this formalism has, I think, very little to do with the thermodynamics or thermalization. It feels that way.
Yeah, so maybe maybe my approach is actually come from the resource theoretic background. So like in the resource theory of thermodynamics, people usually start from like the you just identify what's your is your free state, and then you just build your whole framework upon this. So it's
Yeah,
kind
that
of
is
different
fine.
from the traditional thermodynamic approach. Yes.
No, no, I'm fine with that. I'm just saying that in thermodynamics, they have other goals in mind, right? So they are interested in work extraction that explicitly depends on Hamiltonian. So you are not worried about any work extraction kind of scenario. So your measures may not be directly related to work as such.
Yeah, so like this RT, I have said that this relates to like the work you need to prepare this state from the thermal state.
Yeah, but maybe a very loose
Yeah.
bound because it cannot be tight bound, even though it might be related in some sense. But
Uh,
like tight,
you mean this bond is not tight? Yes, I agree. Like this
no, no,
bond
no,
is
no,
not.
no. I meant the relation between RT and the extractable work. That
Oh, okay. So then that is actually a precise result. It's not a bound. So here, so when rho is incoherent, then from this paper, you can actually find the work of formation is actually given by KT log 2 times the like the
mean or
mass
max
relative
relative.
entropy. Yes, and then you can see this are just there is a equality between these two, so there is no bound
Right.
for it. Yeah.
But this max result is for asymptotic case, and yeah, that is why
No,
I'm having a little bit problem.
no. This is for one shot case actually. So the max
Oh,
relative
right,
entropy comes from the one shot, and then if you go to asymptotic limits, you will reduce it to the standard relative
right,
entropy.
right,
Yeah.
right. Right. This part is a little bit strange, yes. In any
Sorry,
case,
what?
this relation, sorry, in any case, this relation is always true that I know that 1 plus robustness measure is actually related to max relative entropy. So this is irrespective of any resource theory actually. Yeah, yeah, it's okay. I was
Mm.
just like I'm very puzzled calling this thing thermodynamics because without role of Hamiltonian, it's a little bit bothersome. Yeah, thank you very
Yeah.
much.
Yeah. Also, thanks for your comments. Yeah, I don't know how to answer this. Yeah.
Okay. Any other questions? If not, then let us thank Yutong again. And yeah, thank you.
Yeah. Thank you
Yes.
for the invitation again. Yeah. Thank
Thank
you,
you. So
guys.